All right, let's just take a look and go over this stuff for the review so that you can understand what's happening for your quiz, just to go back over the things that we've been going over the last few days. So when we solve a system by graphing, that obviously means you need to make the graphs. When you've solved them for y and they're linear, then they have a slope and they have a y-intercept. Make sure you don't confuse the two of them. So you would start with your y-intercept on the y-axis and then count for your slope, so that when you have these graphs come out, and there's technical difficulties that this is not moving. I'm not quite sure why. Hold on a minute. Wow, everything is completely locked up. Alright, so things are not locked up anymore. I don't know why exactly they locked up, but this is technology for you. Okay, so when you graph, starting for this one, we'd start at -4, and then the fraction up 3 over 2, up 3 over 2, up 3 over 2. It does have a positive slope, so once you've made your graph, just double check to make sure that you've done that way. And then starting at 5, down 3 over 1, down 3 over 1. Draw the other graph, and since it says solve by graphing, your choices are limited. Your choices are only to do the graph and then say where the ordered pair is, where it connects. So 2, -1 is the solution. It's the point that works in both. So that's our first method, just as we quickly go through. And if you don't have a chance to write this all down right now, don't worry about it. As I said, you'll get a chance to go through and slowly check for yourselves. So this is more of a paying attention type of a time rather than a writing. Solving by substitution or elimination. If you're given the direction to solve by substitution, you have to do it by substitution. This one's set up for substitution. If you're asked to do by elimination, you have to show that you know that skill. So just as a quick example, you would take this number or this expression and substitute it in where you see the y. So when you do that, watch out specifically when you substitute it in. Watch out for like this minus here. Make sure that you distribute it so that you have plus and minus here. And then putting your like terms together. 3 and 2 give you 5. Adding the 4 to both sides. And your solution in this case comes out to be -1/5 or -0.2. Remember, you're not always looking for it to be... this one's if it says substitution or elimination, you can have your choice, and you can do either. But this happens to be an example of substitution. So we have that. Then whatever answer you get, even if it is a decimal or a fraction, you have to plug it back into the other equation. And then when you plug it back in, you do the work until you have a solution, and even if it's decimals or fractions, you make it into its ordered pair for its final solution. So substitution and graphing so far. We'll take a look at elimination. Now on this quick review, we have the simple eliminations where something's already set up to eliminate without multiplying, but keep in mind that you are responsible also for if you need to multiply in order to eliminate, that you could do that as well. So right here, the -y and the y are set up to eliminate. So when they do that, they cancel out, and you end up with the x's adding together and then the other numbers adding together, so that you get that. And then finally, you do have to do a little substituting, because you have to go back into this original equation here, put the number in, work it out, multiply your 5 times 2, 10, subtract from both sides, and once again end up with an ordered pair. Even if you're not drawing the graphs, in your mind you're thinking, okay, what I'm really looking for is where these two graphs would intersect, but I'm not taking the time to draw the graphs. This one came out with nice whole number, well, a whole number and an integer, so it could be fairly easily solved by graphing, but just not practical for the other one where we came out with decimals. Another example of elimination here, it's already set up to eliminate, but as I said, make sure that you're also thinking about the ones that you did in the other review assignment for homework and when we did it in class, that sometimes you have to do something. So this also, the y and the negative y will cancel out. But before you do that, we have this pesky little negative 14 that needs to move over to the other side by adding it to both sides. And then it is still set up to eliminate, but sometimes you might have to do that so that it looks like that when you add the 14 to both sides. Then we're able to eliminate easily. The 3 and the 4 give you 7. This gives you 21. But don't forget to move it over so it's in standard form first. Dividing it out so that you get a 3. Take the 3, plug it back into either one of the equations that you like, or even one of the ones that you modified, and then solve, and then write your answer as an ordered pair. So substitution, elimination, solving by graphing, those things are the things that you need to do. Do your algebra carefully. Remember, always do things to both sides to get a variable by itself. And as I said, I'm going through this kind of quickly just to do this and give time for you to ask questions on homework as well. So solving the inequalities. Okay, this is where you've got to graph this one and graph this one. This one needs to be made into slope-intercept form first. It does look like it would be linear to start with, so you would have to do that. And then once you get it into that form, you would graph it and then show where things overlap. And just as a really short version of that, when you get y by itself here, you have to add 2x to both sides, then divide by 5, and we get y equals 2/5 x plus 2. Here's our 2, up 2 over 5. Dashed line because there's no extra little thing underneath. And greater than is the region above. On this one, the V shape for absolute value goes left 2, up 3. Left 2, up 3. There's no numbers out front that would modify it or make it any difficult way to find your V. It's just a standard. But once again, it's dashed because there's no or equal to. And then it's less than, which would take us below it. So the region that is true for both of them is above the line and below the absolute value graph. And so right in here is your overlapping piece. And I know that you did a lot of those for homework last night, and we'll take those questions afterwards, but just here we go. And then last one, oh, not quite last one, but pretty close. Be careful when you do the graphs. Don't assume that it's always going to be like a little area, because this one right here, when you graph this one, negative x plus 2 makes this graph, and we're looking for below. For this one, even though it's absolute value and we go over 3, up 1, turn it upside down, it's also less than, so it's below. So here our overlap is this side of the line and also below the absolute value. So it turns out to be just this region in here. A lot of times people will assume it's the smallest little region, but not always, so please be careful where you look. And you could always pick a test point if you wanted, just to make sure that it worked. So for example, if I wanted to, I could pick 2, -3 here, and do 2 plus -3, if it's going to be friendly to me, which it's not. 2 plus -3 would be -1, which is less than 2. And then 2 -3, 2 minus 3 is -1. Negative of 1 would be -1, so 0, and 2 -3. -3 is less than our -2 that we got. So it does work out. That point would give us both equal, so you can always do that. And then the other one is, notice I said it's a new problem because it's almost the same. What's the difference between that problem and that problem? The shaded part, but why the shaded part? What's the difference in the original problem? Good. Greater than or equal to, rather than less than. So the greater than sends it above the solid line right here, above the solid line. And so above and then under the absolute value makes our solution be this little thing right here. So it does matter as far as whether you're greater or less, and you have to very carefully figure out what makes sense in those. Okay. And then just about ready to wrap up the recording, if it's recording. Hope so, since we had that technical glitch. We'll see. So also you have to be able to graph coincident lines or parallel lines. I don't think there's a graph there for you, but just so you can see, if I tried to graph this one, what would happen when we solve it for y equals, you would have the same slope. So when you graphed and you find that they are parallel because they have the same slope, how many solutions would be for that one? Actually, this one has no solutions. Parallel lines have no solutions. Yeah, if it's parallel, you'd have to say no solution. And if it were coincident, you would say infinite solutions, yes. Independent stuff, I will double check with you as far as on that. I don't believe so, yes. Mm-hmm. Yes, if it was like a greater than or, yeah. So what he asked is if this was like a greater than for this one and a less than for this one, it would be no solution. This is equals though. And when we have equals, you can have no solution as well when they're parallel. Okay, and what was your question again? The independent thing. Okay, thank you. We'll get that in a minute. So this would actually, just so you know, this one would be independent and inconsistent, just to go over those phrases for you. Independent, inconsistent, because they're not the same line and they don't have a solution. The coincident lines, in other words, you solve them both and they come out to be the same one. They would be dependent and consistent because they have infinite solutions. The answer to this one would be infinite solutions. And they're, like I say, they're consistent and dependent. And then the ones that have one solution, just to remind you, are independent and consistent. So that you have those words. I know we had put those out there. All right, so that's that. So let me just see if it's